We will now look at how to find global maximums and global minimums of a function. Recall, we said that a function has a local minimum at x equals c if f of c is less than or equal to all other values of f of x near c. And f of x has a local maximum at x equals c if f of c is greater than or equal to all other values of f of x near c. And remember, we saw that at both local maximums and local minimums, f prime of x equals 0. And so we made the definition, if f prime of c equals 0, then x equals c is called a critical point. We will now give related definitions. We say that f of x has a global minimum at x equals c if f of c is less than or equal to all other values of f of x. Notice that this is the same definition for our local minimum, except we have gotten rid of the condition near c. So this simply means that f of x has a global maximum at x equals c if f of c is the smallest possible value. Similarly, we say that f of x has a global maximum at x equals c if f of c is greater than or equal to all other values of f of x. Again, getting rid of the condition that we have to be near c. Let's interpret this using the graph of f of x. Notice here that f of x has two local maximums. However, the one on the right is larger than the one on the left, and the one on the right is the largest possible value of f of x. So it is a global maximum. What about its minimums? This function f of x has a local minimum at one point. However, since our function continues down to negative infinity, there is no global minimum. That is, no matter what point we pick, there's always another one that's even lower. However, if we were to cut our graph off and only look at x values between a and b, then our function wouldn't be going off to negative infinity, and it would have a local minimum. In this case, the global minimum is at our right-hand endpoint, x equals b. This idea leads to a theorem called the extreme value theorem. The extreme value theorem states that if f of x is continuous on a closed bounded interval ab, then f of x has a global maximum and a global minimum on the interval ab. Before we look at examples of this, what do I mean by the words closed and bounded? Closed means that our interval ab includes the endpoints a and b. And bounded means that neither a or b are infinite, so a and b are real numbers. Notice that the extreme value theorem only tells us that a global maximum and global minimum exist. But how do we find the global maximum and minimum? Let's start with an obvious but useful statement. The global max and min is either on an end of the interval or in the middle of the interval. Why is this useful? Well, let's look at the two possibilities. If it is on an end of the interval, then it is either at x equals a or x equals b. And if it is in the middle of the interval, then it must be a local max or min. But whether it is a local max or min, it must be a critical point. So our conclusion is the global maximum or minimum of f of x on ab is either at x equals a or x equals b, one of our endpoints, or at a critical point. So to find the global max and min, we need to find our endpoints a and b and all of the critical points. Let's now look at an example where we find the global max and min. Let's find the global max and min of the function f of x equals x cubed minus 9x squared plus 15x plus 6 on the interval 0 to 8. To solve this, we first need to find our endpoints and the critical points. On the interval 0 to 8, the endpoints are x equals 0 or x equals 8. To find the critical points, we need to find when the derivative f prime of x equals 0. Computing the derivative, we get that f prime of x equals 3x squared minus 18x plus 15. To solve the equation 0 equals 3x squared minus 18x plus 15, we can either factor or use the quadratic formula to find that x equals 1 or x equals 5. So we found the endpoints x equals 0 and x equals 8, along with the critical points x equals 1 and x equals 5. So now the question becomes, of the points x equals 0, 1, 5, and 8, which is the global max and which is the global min? To find this, we simply need to evaluate f of 0, f of 1, f of 5, and f of 8, and find which is the largest value. That will be our global max, along with finding which is the smallest value, which will be our global min. I want to remind us here that we are evaluating the function f of x, not its derivative. So evaluating, we find that f of 0 is 6, f of 1 is 13, f of 5 is negative 19, and f of 8 is 62. So this means that the global maximum is the value 62, and it happens at x equals 8. The smallest value of f, the global minimum, is negative 19, and it happens at x equals 5. So this tells us that on the interval from 0 to 8, the largest value of f of x is 62, and it happens at the endpoint 8, and the smallest value on the interval 0 to 8 of our function f of x is negative 19, and it happens at x equals 5. Let's now look at another example. Let's find the global max and min of f of x equals x cubed minus 9x squared plus 15x plus 6 on the interval from 0 to 4. Notice this is the same function, but on a different interval. Again, to solve this, we need to find the endpoints and the critical points. Since our interval has changed, the endpoints now are x equals 0 or x equals 4. We found previously that the critical points happen at x equals 1 or x equals 5. But notice that x equals 5 is not in our interval from 0 to 4. So this cannot be a global max or min on the interval from 0 to 4. So now the question is, of the points x equals 0, 1, and 4, which is the global max and which is the global min? Again, to find this out, we need to evaluate our function at these points. We already found that f of 0 is 6 and f of 1 is 13, so all that's left to find is f of 4. Evaluating f of x at x equals 4, we find that f of 4 equals negative 14. So the global maximum of f of x on the interval from 0 to 4 is 13, and it happens at the local maximum x equals 1. While the global minimum of f of x on the interval from 0 to 4 is negative 14, and it happens at x equals 4. So we found that the largest value of f of x on the interval from 0 to 4 is 13, and it happens at x equals 1. We also found that the lowest value of f of x on the interval from 0 to 4, or the global minimum, is negative 14, and it happens at the endpoint x equals 4.